after that. Okay. So it's going to be a bit of a back and forth with me seeing you and me seeing the code. I can only see one of the two things. So so who's a Clojure developer here? Just show of hands, or an enthusiast or a hobbyist. What other languages are there out there?
There is no other language.
No other language. This is just Clojure. Awesome. So I think, is everyone familiar with Lineagen or some variation of that pronunciation?
Yes.
Lineagen. It's the thing that you get the REPL with and the thing that you hook up with Maven. So I'm going to be using Lineagen. So I guess this presentation is basically as if I was over your shoulder and just leading you in the first steps of typed Clojure. So just really simple stuff to start off with, things like how to get the right dependency strings and all that. So step 0 is go to the typed Clojure, that's the first thing, is that there are two names that typed Clojure has. One is typed Clojure, and that's the kind of the overall project, the calculus and the proofs. And then there's core typed, which is the actual software. So this is the dependency string that you want. This is the thing that you'd copy into Lineagen. And I'm just going to go over to my buffer. And by the way, the code that I'm working with today is actually online. You may want to just, I encourage you just to grab it. Let me just find it. So my GitHub name is Frenchy64 and Boston Clojure Group presentation, contract.typed. So if you clone that, you can basically follow along, or you can read it later or anything like that. So what we're going to do, we're going to build what is in this library from scratch. But again, step 0. So what we've done, we've pasted in our dependency string in Lineagen. All this does is gives us an extra jar called core typed. So core typed is a library. It provides an optional type system for Clojure. So that means that you would notice that we have the normal Clojure compiler. So we can, when we call compile, we're really compiling Clojure code. So you can think of typed Clojure, this dependency, as a thin layer of macro magic on top of Clojure. And it's not really that magic. You can browse exactly what the macros are doing. But the macros basically allow you to annotate your code. And that's one of the things that you do when writing typed Clojure code, as opposed to Clojure code. With Clojure, we're in dynamically typed land. We might use contracts or generative testing or unit testing to verify our code. Typed Clojure gives us static type checking. And yeah, we need to very often give high-level annotations. Okay, so that's spill out of the way. If you've used typed Clojure before, there's been a few changes in the last few months. One of them is that typed Clojure has been integrated into the Clojure compilation process. What that means in practice is when you require a typed namespace, it will actually type check it, which wasn't the case before. Before it was, you had to actually explicitly call the type checker. So without talking anymore, I'll show you a minimal typed Clojure buffer, a typed Clojure file. So here's a namespace. Can everyone see this high?
Yep.
Do we need more font, bigger font?
No, it's good.
No? Excellent. So we have a plain namespace, this is contracts, and this is the talk buffer. I'm going to be chucking stuff into here. First thing we do to create a typed namespace is this. So when we call require, I think we've actually type checked, and we can verify that by writing some ill-typed code. So let's write a function that this computation will be delayed. So in untyped land, this isn't a type error because it never gets run, but in untyped land, it never gets run. But in typed land, we can perform some static analysis. So hopefully if this works, we should get a type error. Yes, okay. So what I'm gonna do, the tooling hasn't quite caught up with where I'm at with type Clojure. So what I'm gonna do, every time that I type check things, I'm just gonna go to this buffer over here. Sorry, this lineagen REPL. And this is just a normal REPL. This is how I started it. I cleaned it and REPL. So I'm going to require contract.talk, and I'm going to reload it. Okay, so here's our first type error. So static method inc could not be applied to arguments. And the way you read this, we're at line 4, column 2, so this coordinate here. What this increment var does is actually inlining this this Clojure method. So what this error is saying that the domain of this method, or the argument, the expected argument type, is a number. What we've given is a symbol. Clearly, this is bad. So the way we fix this is just increment 1 instead, and we can require, and this is basically nil is the normal return type, the return value for require. So once we've got nil, that's good. Okay, so any questions at this point?
No.
Awesome. So once we start actually writing real code in type Clojure, we probably want some of the nice macros that type Clojure gives you. So I'm going to alias Clojure core type as T. So here's how you annotate a var. So let's have a variable f. Int to int's always a good one. Here's a function type. Int to int function type, and we're going to use the normal Clojure defin. Ink's boring. Let's add 42. All right, this should type check. Right. So what's happening here is that we've given expected type to f, and then we've written the implementation of f. So one of the rules of typed Clojure is that when you write a function, you have to annotate its arguments. So it has what's known as a local type inference, not global type inference. So it's kind of like Java and Scala in this sense. So this annotation here, this int, is very much needed. So what's the best way to... Yeah, so if we didn't have this int, the error we'd get is we cannot add any to 42, because that's what this this function argument would default to. It was the most permissive type. So that's annotating top-level functions. So we've... I think we can get into the fun part. Yeah, let's build a contract system. So what I've been doing recently is moving typed Clojure from being optionally typed to gradually typed. What that means is that if something's optionally typed, it's just I like to think of it as a linter over your code. It doesn't actually change the result of your code, and you can't really depend on it. You can't generate faster code because of a linter, because it only gets, it's a completely offline process. So that's an optional type system. Gradual typing integrates the type system into the compiler. So it's just like a normal typed language like Java or Scala or ML. And gradual typing in particular allows us to care about language boundaries. So if we have untyped and typed namespaces talking to each other, the typed namespace actually is going to expect certain invariants from the untyped. So if the untyped namespace passes a I'll show my face instead, because since I'm doing this. All right, so we have untyped and typed namespaces. So say we have a typed namespace and an untyped namespace over here, and the untyped namespace is sending over an int, right? The typed namespace is expecting an int. So what gradual typing says is that there's a language boundary in between these two namespaces that basically mediates the interaction between the two. So for example, if the untyped language sends over nil, the language boundary will say, no, this should be an int, and then it says, this was your fault. But if, for example, a untyped function passes an int-to-int function over, what actually happens at the language boundary is that the function is wrapped in a proxy, basically, that asserts that int-to-int contract, and it floats around in typed land until those contracts are checked. So those are two interesting cases in contracts. So what I mean by contracts is what this language boundary is actually doing is checking values at runtime, and it checks their shape and it checks their behavior. So by shape, I mean you could have a tree, or immutable tree, or a vector. So anything immutable in Clojure, we can just check straight up because it's not going to change in the future. We don't need to proxy it. So that's checking its shape. So we can also check its behavior. So if we have a function, we can check if it actually returns an int. And that's actually the interesting case. So what we're going to do now, we're going to make a contract system and type check it at the same time. And maybe I'm kind of practicing my teaching of contract systems as well, because I only just recently learned what they really do under the hood. So hopefully, so please stop me if, one, you don't understand what the code is I'm writing because it's in typed Clojure, and two, if the concepts of the contract system are confusing. Okay, let's do it.
Quick question. Is when you have the contracts, is the type checking or the checking happening at compile time or at runtime with the wrapped code that you're talking about?
When I was talking about this language boundary, this is all at runtime because you can't. The intuition is one reason is we don't necessarily have the source code for the untyped language, right? We do for the typed language because it's being shoved through the type checker and we can check the actual source. But yeah, this is something that basically has to happen at runtime. Yeah, good question. All right, so this is what I forgot a step. Let's share the screen again. Is that showing?
Yep.
Thank you. All right. So recently I extended type Clojure to include contracts, and all I did was basically open up the Racket contract system, which is another language based on Scheme, and copy that. So we're going to build a contract system that basically looks like Rackets. So here's the integer contract. What this does, this contract form takes a contract and a specification and a value, and then returns a new value or a possibly new value that has some correspondence with the input, and basically asserts that the value jives with the shape and behavior that's required here. So what actually happens if, oh god, my Vim is gone crazy. All right, that Vim needs to quit. Let's try again. Thank you. All right, so that's what happens when this contract system passes. So contract, if we pass it nil, we have this concept of blame, and blame's all about pointing fingers. So we can blame a particular party. So for example, if this was a untyped variable and we called it and it wasn't integer, we can blame the untyped namespace. So yeah, this is basically the depth I'm going to go into blame. It's basically we're going to have two parties, the person who sends it and the person who uses it, and one person is to blame. Okay, so I'm going to start bottom up. I'm going to create a contract generator, and it's going to be called make contract. But in type Clojure, a good way to start designing things is to write the types out first. So I just happen to know exactly what I want this to do. It's going to take keyword arguments. So we can annotate this variable to take optional keyword arguments. And it's going to take in first order predicate, which is something, projection, which is something else, and a name, which is something else. And then the return value is going to be some contract, which we haven't defined. So a bit of wishful thinking going on. I don't have these defined yet, and I haven't explained them. But what we're going to do, we're going to fill out these with type aliases. So in Clojure, when we make new data structures, we don't really define new types. We use maps. So that's what we're going to do here. We're going to use maps to represent these concepts here. But it turns out these concepts aren't actually maps. But okay, first order. What we're going to do, we're going to find a type alias called first order, and it's going to be a function from any to any. That basically means we can pass anything to this function and return anything from this function. And we can add a doc string to type aliases. So what's a good documentation string? I haven't explained what this does yet, so this better be good. So a first order predicate is a one argument function. Notice how the type and the documentation can complement each other. So I'm in the middle of this typed versus untyped religious war, and I accept all software engineering strategies. So a first order predicate is a one argument function. Basically what I want, for integer C, I want the first order predicate to be integer. And for a function, I want it to be ifun. So it's going to be an approximation that can be checked immediately. Yes, a first order predicate is a one argument function that approximates a contract and can be checked immediately. So notice that identity and plus are both going to be checked with the ifun predicate. So there's going to be some approximation going on here. This isn't entirely clear. Hopefully in about once we've gone through these other examples, it will be a bit clearer. So a projection, it's going to take a thing called a blame and to any. So this is a curried function. So this is a function like a int to int or any to any, but this is a function that returns a function. It takes in what's called a blame object, and we're just going to assume that blame is already defined. So a projection is a curried function that takes a blame object and returns a takes a blame object and a value and returns a new, possibly wrapped value. So, for example, this projection for 1 is going to be 1. The projection for going to be the contract of projection of 1 is going to be returning 1, and then if we're checking an int to int function, it's going to return another function that wraps it in some way that we're going to see later. Okay. Notice what I'm doing. I'm just I am skipping the part where you think about the problem because I know the answer. But notice what's happening here, where we're not putting any types in the actual in the annotations. We're using aliases and we're documenting them. And I find this strategy works pretty effectively because what actually happens is def alias adds to the documentation metadata of projection. So when you hover over, if you use cursive or Vim or Emacs, however you get the metadata of the documentation, the metadata of a var, that's how you're going to get this documentation string. So it's a very useful thing to do. What a blame is, let's see. Okay, a blame has two parties, a positive and a negative party, and it's basically the two people that are involved in a transaction. Two parties. A transaction. So what this syntax is here, this is called a heterogeneous map, and this basically this allows us to type check values such as this. So a map with keyword keys and known values. So positive key corresponds with here, and this string. Yeah, so it's probably intuitively obvious what's going on here. You've probably seen a similar type in other languages. Okay, after all that, we can start writing some code. Okay, so in Clojure, we write keyword arguments like this, and we don't have to do anything different in type Clojure. So we the first order, get the projection out, and the name. Let's just say the name is a string. Maybe it's a good time to compile. Contract. I haven't defined contract 32. Ah, yeah, what is a contract? Contract is basically the same as these arguments. Projection takes a projection and has a name. Yeah, okay. Don't want to be redundant, so let's define name to be something. A contract name. Contract named name that so a contract that checks its value with these two functions, which we'll see how in a second. All right, now type Clojure. Will you let me compile? Type mismatch. Oh, this is good. This is saying the function at 44 actually returns nil, and we say it returns a contract. So this is a kind of type-driven development. You can think of it like that. Kind of pausing. One way to, if you've heard of, I think it's called hole-driven development. This is how to do it. Just throw an exception here. and everything will just work out, because type closure acknowledges that this won't return a value. So we can assert it to be anything because it's not going to return anything. So but the intuition is that runtime, you get an exception saying like to do, and then you'd resume. So this is a trick people use in Haskell as well, and it works just as well here. Okay, let's write this code. Oh, I'm missing something. Okay, so in Java, we have nullable references. In type closure, we do not. So we have to explicitly use null or nil here. So the first order predicate, I'm allowing users to not only optionally pass it, but also be able to pass null or nil into this position. So this is how we do it. We use the union constructor, which is under the typed namespace, or the Clojure core typed. And all of these things are optional. But notice that we want to create a contract at the end, and these are not nullable. So we need to refine these types just to the non-nullable versions. Okay, so name. So it's either going to be the name, as in this name here, or let's say anonymous. It's going to be the anonymous contract, and there should be a string. So at this point in our program, type closure infers this to be of type string for obvious reasons. So the first order predicate, this is a very similar thing. So it's either going to be the thing that we pass in, or what's the most permissive one argument function that returns a Boolean? Well, it's something like this. And projection is where it gets a little trickier. Either we pass in the projection, or we're going to, let's split our buffer and just use the type to drive how we build this projection. And we don't even need to particularly understand what this does yet, but we know it's a function that takes in a blame. Okay, well, it's a function that takes in a blame. So the way we can do that is using the typed macro, the typed fn macro, and takes in some blame, and we annotate it as b. And this returns another function that takes in something and returns something. Okay, so it takes in something, and if we really want, we can use any explicitly here. But just for the sake of demonstration, if we leave this empty, this is actually the same as annotating any. So let me just move this down a bit. And then this, so we're working on this thing here. It takes any and returns any, so it can return some x. Actually, the correct implementation for this here, what this projection is supposed to do, it's supposed to check the first order predicate. So for the int contract, it's going to be integer question mark. So what we're going to do, we're going to ask if the first order predicate passes on this x. And if it is, we're going to return the x. And this is the x, this x here, this is where x is inputted, and this position here, this is where the output goes, just for some perspective. And if the first order predicate fails, so if integer question mark fails, we're going to blame someone. So let's imagine that this function exists, throw blame. Okay. And we've got a name, a first order, and a projection, and we need to return a contract, okay? Because we know by the return value here. So let's go to the contract annotation. Okay. Do we have a first order thing? Well, yeah, it's called first order because we've ensured that it's not null. And a projection, we can use projection and name again. So I know this is going to throw an error about throw blame. So let's just declare throw blame up here and just annotate it for someone else to deal with it in the future. And nothing. Throw blame just throws an error. Okay. Let's type check this. Okay, so we got a duplicate var annotation warning. What this means is that we have changed this this annotation between compilation between type checking attempts. So before, remember, we added this union nil, and if we actually type check this again, we won't get the duplicate var annotation. Okay, so this actually type checks. Maybe this is a good time to ask if there are any questions.
Yes, I have a question.
Okay, let me just show my face. Or is it about the code?
Yeah, it's code, so it might be better. Go ahead.
All right.
So I just want to make sure I'm following so far. You had defined contracts to be a map with 3 keys, correct?
Correct.
So when that type checks, is it checking for those particular keys to be in the map?
Yes.
It is, okay.
Yes. Here's an example of a contract. A first order, takes something, projection, takes a blame and something else, and a name is me. This is a type contract.
Okay, but if, for example, one of those keys was different, like maybe like the hyphen was missing from first order, that would not type check?
Sure, let's try it. How about we comment this out and we use the andForm macro to assert that type Clojure is confident that this is actually this type. So this andForm says this value, type checks is this type, and it clearly is not. So let's type check it. Okay, so we have a large error. Maybe I should try again, like this. Oh yeah, it is actually on one line. Yeah, see what's happening here? We're expecting this name contract, but what it really is this HMAP thing with 3 keys. Notice that we have a HMAP mandatory keys, and we found first order, and name, but there's no projection. All right. Does that answer your question?
Yeah, follow-up question though. You had mentioned a few minutes ago that the values for the contract in the contract map were non-nullable. Is that correct?
Correct.
But then you later wrote that the unions allowing them to be nullable in the make contract function.
Okay. Are you asking why I put that in, or?
Yes. Yes.
Okay.
Non-nullable. Why is that there?
All right. All I wanted was someone to be able to call make contract like this to get all the defaults, right? And also do this.
I see.
And if we actually type check this, it should type check once I comment out the other bogus example, or actually make it type check. Let's do that. That's more fun. Name. Will that type check? Yeah. So both of these things type check. Let's, for fun, let's just get rid of one of these. So first order must be non-nullable, and clearly first order is not. It's nil. So let's see what happens. So again, we've changed the annotation, so we get this warning. But okay, we got various errors, but which one do we want? 61, 63. Oh, what am I looking at? Cannot invoke type nil. Maybe we found a bug. That'd be cool. First order. Yeah, that looks like a bug, and I think it's to do with this this reloading stuff. But anyway, intuitively, this should not allow nil here, and it kind of blew up in here for some reason. Let's just see if we can recover where we were. Yeah, this feature here is like existed for like a month. So if there are any bugs with that, it's probably my fault, not yours. Any other questions? Or did I sufficiently answer that one?
You did. I actually have another question. If I feel like the bog is down a little bit more.
Go ahead.
So someone asked a question earlier that confused me. I just want to clarify it. So I understand that the type checking that type Clojure is doing is happening at compile time.
Yes.
I think you said that the this contract checking mechanism is actually happening during runtime. Is that right?
Yes.
Can you just say a few more words about that? I'm not sure I understand why that would be the case.
Have we seen that yet?
Okay, there are. This is kind of a meta thing. We're building a contract system, but type Clojure also has a contract system, which I haven't shown yet. So all we're doing, this is, you can just imagine that this is like an interpreter, or we're writing any other code. What's the best way to explain this? So maybe, is it easier if you just ignore like what exactly we're doing here and just the fact that this is just typed code, or is it more that you want me to do some more hand waving and show you when things actually happen at runtime with the gradual typing?
Well, are you going to use this make contract function?
Yes.
So I think that will probably show a run,
okay.
Right?
Yeah, let's do it. Let's do it. It's much more fun once we use this thing. And it's actually much more fun if we write a macro to actually... all right, so I'll write this and I'll ask for more questions later. So we have, remember the syntax we were talking about, contract takes in a contract and the value. So in type Clojure, we can just write contracts, we can just write macros and then not type check. So this contract is going to take a contract and a value, and we're just going to recursively call this for reasons that will become obvious in a second. The reason is that we have an extra arity here. So this contract takes a contract value and blame object and returns a new value that satisfies the contract or throws a blame error blaming the blame object or using the blame object. Okay. So the way we do that is we, first thing we need to do, if we, I'll just realign my buffers. Let's go check the type of contract. Okay, so we have a contract C. What we want to do is we want to get out this projection, pass it the blame, and then pass it the value. So the way we do that is we put in the contract, get out the projection. So now we have this thing here, this function. Then we're going to invoke this function and give it the blame object. And now we're left with this function here. And we're going to give it the value. And the return type of this should be, well, let's try it out. Let's write the simplest int contract. We make contract, the name is going to be int c, and I'll just align this, make it a bit easier. First order check is going to be integer. Okay. And we can finally call this int c1. The thing is, whew. What does this mean? Wow, no line numbers, brutal. Oh, projection. Maybe that was it. All right, well, one way to diagnose things is just to comment things out until it stops breaking.
Shouldn't the NC name be a string?
Yeah, good one. Yeah, thank you.
Also in throw blame.
Say again?
If you look at throw blame.
Oh, yeah. This should.
Shouldn't that be a key? The arrow be a key?
Yeah, that is not defined yet. But let's just try your first suggestion. Oh, yeah, excellent, thank you. Yeah, and your second suggestion is going to blow up round about now, I think. Function well, oh, okay, maybe it never got that far. Contract is not a function. Should say something like throw blame is not defined, maybe. Oh man. All right, I'm gonna cheat. Let's look at the actual code. Projection, BC, make blame. Positive cast. So it was definitely this form. So yeah, okay. This is like a typical problem with languages that have macros and half-finished type systems, is that line numbers have disappeared. It's calling array map, but it's not really clear where it's calling array map. I'm assuming somewhere in here. All right, maybe I should give up and go to the actual solution, because this is basically the same stuff. This all looks familiar. Okay, so where we were here, the contract. Let's just comment out the rest of this. Okay, contract dot typed, I think is the actual. This is the code that's committed. Okay, that actually type checks. Now let's try and write the thing I was trying to write. Make blame could not be applied to arguments. Yeah, this looks wrong. Positive. Yeah, okay. So this is expecting a symbol, and I'm giving it a string. So that's probably what's happening here. give it a symbol. So blame is actually slightly different here. Actually name. Name is now either a symbol or nil. So let's context switch to that. Why wasn't that caught before? Maybe I just wasn't calling it properly. Okay, so that actually type checked. Now let's try and do what we were trying to do for 10 minutes on the other side. Oh my God, something happened. Okay, this is where the magic happens with contracts. When you ask for something that's an int and you get something that's not an int, you have these positive and negative blame parties. This is basically saying the problem is whoever casted this is to blame. So whoever wrote this code. It's not quite as interesting when you write these things down directly. But let's just comment that out. It might be useful to assert that this equals 1. And this isn't particularly interesting to do with type systems, but what else could I do? So if I want to actually, so this is a unit test to see if this contract system succeeds when it's actually passed it. How do we test? Go on.
What's int C again? How did
sorry. Int C is a contract. Its name is int C. Its first order predicate is integer ? And we leave it to the default projection. So what actually happens is that contract int C1, it's basically this function, takes in a blame, takes in the number, and then if it's an integer, return the integer, otherwise throw blame, B. So then we pass it the blame object. Let's just assume this exists. And then we pass it the number. All right. So yeah, this is basically what the int contract is. Does that make sense? Yeah.
The contract macro is doing the checking, and int C is the contract that's checking one against?
Yes. All the contract macro is doing is extracting this function and then passing it the blame and the value. Yeah. So we can see it in action here. This is the function. It gives it the blame, gives it the value. And yeah. Okay, so this isn't as interesting. I'll skip that. Okay, so I guess to finish off, I'll show you an interesting case. So here's a case for the int-to-int functions. So say functions like plus or inc are int-to-int functions because they take an integer and they also return one when you give them one. So the way we're going to do that, we're going to make a contract called int-to-int. Let's call it int-to-int C. The first order predicate is going to be ifun. So actually, this is an implementation detail. We can ignore this. The projection is where it gets interesting. And let me delete this so the punchline, well, one of the punchlines aren't given away too quickly. Okay, so the projection takes a blame, and then this, let's just show an example. Contract int C, what do I want? Add one, what's it called? Inc. Sorry, I've been programming in Racket. It has an add one function. Anyway, this contract thing here, it grabs this blame function, and what it does, it takes in the blame, and then it passes in the function f. So in this inc, when we're contracting this inc, this f is inc. It's incrementing. So if you remember the structure of the projection, the thing in this body is the value that we return to replace f. So this should be an int-to-int function. What we need to do, though, is check the input and the output. So this x is going to be, if we actually call inc, this 1 is this x here. So we are creating this kind of wrapper around inc. But what we're doing is we're checking x before we pass it. So this is what happens here. We're checking that x is an integer. But the interesting thing is here, we're swapping the blame, and I'll show you what swap blame is. All it does is that whoever's positive is now negative, whoever's negative is now positive. The intuition there is that the positive blame is the person who gives you the value, and the negative blame is the person who uses the value. So if the person uses a function incorrectly, they are to blame. So that's kind of the intuition. It just points the finger the other way. But once we've got an x that's contracted, we just call the function, and then we assert that the return value of this function is going to be an integer, and we blame the person who gave us the function in the first place, because they have full control. The person who gave us this function has full control over over what this function returns. Okay, so let's compile this and see what happens. Okay, I think this is left over from my scratch. Blame, 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 blah, blah, blame. Too much documentation. Blame, 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 blame. This thing. Let's just comment that out. Oops. Okay, so line 257, column 35. So I'm assuming that's this. Okay. Cannot invoke type any. So remember, if we don't annotate a function's arguments, it defaults to any. But this has to be a function of any to any. So what we need to do in type Clojure is cast the value in type Clojure. So we use the cast function. So we cast it to be a any to any function. So what this does, it convinces type Clojure that we're allowed to call this function with an argument, hopefully. Okay, that actually worked. Okay, so does anyone have questions?
Could you spend a few minutes describing what are the core functions of core.type?
Yeah. What's the easiest way to do this is api.typeclojure.org. Yes. So here's the documentation for type Clojure. And you see there's a bunch of types on the right-hand side. And you might recognize one. Here's string. So if we click string, it has some sparse documentation. But it's actually a string. And notice it says type alias here. But also in here, there are types, and there are also functions and macros. We've seen and form that takes in a type and a form and type checks it, and annotates a var. Let's see, what's some other interesting ones? Defen, that's probably one that is a fan that lots of people like. So instead of writing this, we can write this instead. Let's just increment it again. So it's just a way of annotating things.
So return type is after the brackets, the square brackets?
Yes. Okay. So the convention here is the turnstile goes after the form that would normally take metadata. So for example, X would normally take the metadata, so you would intuitively think this would be the annotation, but it goes after. So usually it might go here, for example, but it goes after. So that's the convention that I've tried to enforce. It's not what schema does, not what anything else does as far as I know. But yeah.
But it makes sense. It makes sense that you're putting it after every form that way.
Yeah, I think a historical note is that it was actually before, and then schema copied the old version, and then I changed it to this new version. But yeah, anyway.
But you can just use a normal defn and then just annotate rather than using that form too?
That is correct. So here's another way of doing it. You can do def, and then like that. These two are effectively identical, or you could, yeah, again, you could have the annotation as before. Forget about and the arrow, you can either use keywords or symbols. I like to use the keywords because it's in a different color, but it doesn't really matter. Yeah, all of these things are identical. I prefer this. It's hard to say why. Maybe it's because it looks like I'm writing Haskell, and that's supposed to be amazing. So, so it makes me feel better about myself. No, maybe one serious plus to using this is that you can see the entire type very easily. And once you get into more complicated types, which is actually a very good demonstration right now to do, is we can write function intersections. So say we have, let's start with the untyped version. Say we have function f that is overloaded. It takes an x and it increments it. It also takes a string and an x, and then says hello to the increment, or just says hello to this string, I guess. Okay, so anyway, this is kind of dumb, but just bear with me for a second. This is what f looked like before, so this is where the f goes here. So the way we overload things is we use a function intersection. Let's actually compile. Let's do this. And int, no, this is a t string. And hope everyone cross their fingers that I haven't done anything dumb. Okay, so yeah, does that make sense to everyone?
Yeah.
Cool. Yeah, that's actually one feature. If you use core typed at all, that's actually very, very useful to know.
Show us an H map just for like how you do that.
Let me change the way I'm presenting this. I will show you how to evaluate things at the REPL at the same time. Okay, so CF is check form. You give it a value and it checks it and returns a vector of typing information. Usually the first thing's the only thing that's interesting, like it's a value. The rest of this stuff, let's just ignore it. So nil is its own type. A heterogeneous map is a complete H map. What this means is that this is a fully specified map. There are no other entries, so this is clearly true. And if we add entries, notice that it's still fully specified, but we've added some mandatory entries here.
So TCF is like :T in Haskell at the REPL. It like gives you type information.
Yes, yes. Thank you. Yeah. Thanks for reminding me. I forgot. It's been a while. Yeah, so this is CF. The way you use it, like the colon syntax in Haskell, is you just add the type on the right-hand side. Yeah, so you say the map is an int, and it's like, no, it's not. So actually, one thing to note is that this shorthand here is not fully specified. This is partially specified. So this is different from writing complete true. Complete true is how you, complete true means it's fully specified. Complete false means it's partially specified. And you can always lose information. Notice that this is fully specified, so we can forget that it's fully specified. So we're allowed to consider this to be partially specified. And another feature with HMaps is optional keys. It's a good example. Well, foo and bar, of course. Okay. What an optional key means is that it's either going to be in the map with this type, well, not one, or it's not going to be in the map at all. So this is kind of subtle because of the way that the Clojure programmers use maps. And so this is of type because it doesn't have a foo entry. So it does have an optional foo entry. So if we put a foo entry in, it's still that type. So the subtle part is that this is not well typed. And we're expecting a HMap with an optional key of foo, and where we've given something with a mandatory entry that's mapped to nil. So this is kind of weird because getting A from the empty map is the same as getting A nil. So there's this kind of punning going on that typed Clojure does. It makes it a bit, it makes you be more precise about the shape of your data. Yeah, so there's that optional key. There's complete.
Then you would just use the union to get to add the nil back in if you wanted foo to have the nil.
Yes. Yes. Precisely. So we've put back nil in there. So this kind of emulates the this idiom that I was showing before. And you can do interesting things like assoc entries and type Clojure. Remember that, well, this was fully specified, therefore this is fully specified. So the return value is complete, and you have an entry. Hopefully this assoc works. C. Yeah, so we can remove an entry. Merge should work as well. And usually you're working with these kinds of big heterogeneous maps at runtime. So it's useful that these functions can be type checked, but you kind of get to a point where type Clojure isn't useful anymore in its current state. So for example, update in, let's say update in A increment, this doesn't work. Unannotated var update in. And I don't know how to type check this yet. The intuition is, how do I associate this entry with this one? How do I know that this function is being passed one? So that's the problem that I haven't figured out yet. If you're interested in helping out with that kind of problem, please hit me up. It gets pretty fascinating. But yeah, I think, go on.
No question.
Oh, was that just feedback from me? Yeah, I can hear myself now. No, wait. I'll just talk a bit quieter. Yeah, okay, so I don't really have anything else to present. Any final questions?
The contracts thing that you're showing us, that's going to be like, those are actually going to be built-in functions that we can use to specify contracts for our own code. Is that the idea?
Feedback. Can you turn me down a little bit?
Mark,
Yeah.
wonder if we turn the volume down a little bit?
Is that better? Yeah.
Want to ask again?
So is the idea with the contract stuff that you're showing us here is that are there going to be sort of functions built into core type that will provide this contract system for us to use to find the boundaries between type and untyped code?
Yeah, it actually exists today.
Okay, so you're just kind of showing us how the sausage is made here?
Yeah, I'm showing you a very bare bones framework. Let's just go to the actual implementation. This is the actual implementation of contracts in type Clojure in this Clojure core typed contracts library. And yeah, but you don't ever need to care about that. What you should care about are two things. One is in the typed. One is this cast macro, which we can see in the documentation. Cast, yes. And I've used this once already. What's behind this cast is the stuff that I've been presenting. So if you want to cast an int, you can do that. The reason that this hasn't existed yet in type Clojure is because of cases like this and blame, and just general not having time to do things. But now it's here. You can if you have a value that you want to assert the particular a type of, what type Clojure does is converts this to an int-to-int contract and then wraps identity in that contract. So yeah, cast is the way that you get to it by hand, and the other way you can get to it is with this untyped var function macro, which is just arrived, so it has no documentation. So I'll show you an example. Untyped import. Okay. And let's open up untyped here. Okay. So here's an example of the typed untyped interaction. So up the top, we can see we have an untyped namespace. And all it is, it just has two vars in it. One says is actually int, so this kind of alludes that this should be an int, and it is. And this one should be an int, but actually is not. And it's nil. And what's going to happen in typed land, we're going to say, okay, let's require this namespace. This is called untyped, and we're going to require it as u. Then we're going to use the untyped var macro to annotate these expected types. So is actually int, we're expecting it to be an int. Should be int, we're expecting it to be an int. But of course, this is actually nil. So in this function here, good, it's going to, this is the one that actually is an int, so it's actually 1. So if we yeah, this may take a long time, so I'll just leave that in the background. I'll kind of hand wave what's going on here. This is the same as type Clojure adding this cast in, but it actually does this automatically. And it adds the blame as well. So the positive blame is that it's going to blame this namespace for having the wrong type. Or we could blame the annotation, as in this line here, So let's just undo this. What actually happens at runtime is this gets cast to int. If it fails, then we blame the correct person. In bad, this gets cast to int, but it's actually nil. So this will fail, and it should blame, I think, this line. It should say that we're expecting an int, but you've given me nil. And it's kind of a toss-up as to who we should blame at this point, whether, like, did the untyped module really say that this is truly an int? Like, where did it say that in the transaction? Well, we're actually asserting that on line 7, and it's in the typed module. So we can't really say that this untyped module is to blame. So it's kind of a philosophical question there that's kind of interesting. I'm kind of saying it because it's where my mind is at the moment. You probably don't care as much as me, but in practice, this is what happens when you call bad. You get a cast error. So does that give more perspective on what this is for?
Yes. So yeah. The untyped var is like one way that we can provide a boundary between our typed code and our untyped code.
Yeah, untyped var allows us to go in this direction. There's nothing yet to go in the other direction. So we can import untyped things, but we can't export typed things yet. And to give you a flavor of the kinds of things you need to do for exporting, we need to make sure that if we have, say we have some function f into int, my favorite function. How are we going to check that f is not called over here? Well, basically what we've got to do, we've got to export it with a contract that stops people from passing it nil. But what we also don't want to do, we don't also want to, we want this invocation to not check the contract because it's in typed code. We're checking it at compile time. So we want this to be checked at runtime, but this to be checked at compile time. But the trick is in Clojure, F is completely global. So there's no like module system to say, okay, when F is in here, now check it. If it's in here, don't check it. So this is the kind of issue that's why going this way is the lower hanging fruit in Clojure. Does that make sense? Okay, so I got a couple minutes, 2 minutes left. Any final questions?
I had a question. So type hinting gives you performance gains. Do you get that as a free benefit of using typed Clojure?
Yeah, so until very recently, the answer was no. But that was because for the same reason that linters can't speed up your code, type Clojure couldn't speed up your code because it wasn't in the compilation process. It wasn't in the pipeline. So now it's in the pipeline. All it does is add type hints for you. It won't do anything more than that at the moment. So it'll stop reflection errors and whatever speed up you would normally get. So for example, one pet example of mine is the get parent function on java.util.files. So if we'll get parent on this thing, or if we go like, if this was untyped, Clojure would say, oh, we're missing a type hint here. Previously, when you wrote this, type Clojure would say, well, I know there should be a type hint here, but I couldn't put it in because I'm just a lowly linter. So what you had to do before was this. It was this awful, Java file. So there's annotations now squashing the only thing that means anything at runtime. Thankfully, this is all that's needed at the moment to resolve reflection in these small parts of your code, in these small cases. It actually extends a bit further than how type hints infer things. So for example, if this was a union of string and we did a conditional and we checked if f was a string, and we just did nothing and returned. So clearly in this branch, f is going to be a string, and if it's else, then it must be a file. So type Clojure uses this flow checking algorithm called occurrence typing to figure out that that f here is a file. So we effectively get a little better inference than type hints. So a type hint would usually go here. And this is a good example as to why type hints can often lie, because in untyped code, you'll find code that looks like this, because the type hint is being used in the else branch, but it's not in the then branch. But really what this is it could be either a file or a string. So yeah, that's one of the differences between the expressivity of a type hint and the expressivity of a static type. So I have to go now, but it's been great to see you all. Thanks for coming, and thanks for your fantastic questions. Hopefully I can come back again. Yeah, thank you.
That would be great. Thank you very much for doing this presentation.
Thanks. Have a good evening.
You too. Thanks
Yeah.
so much.